Learning target 1.12. I can define and write a balanced equation for beta decay. So here's a picture of beta decay. We have hydrogen 3 turning in or decaying into helium 3 and a beta particle. So a beta particle is sometimes called an electron, and the symbol for it is that. That is the Greek letter beta, stands for B in their alphabet. And why it does this is because the original parent isotope right here, which is hydrogen 3 or tritium, it is unstable. It has too many neutrons. You can see it right here. It has 2 blue circles, which are neutrons, and only 1 proton, which I'll label with a plus since it has a positive charge. It only has 1 proton in hydrogen 3 and 2 neutrons. Too many neutrons in this nucleus, so it wants to kick one out. It wants to take one of these neutrons and kick it out of the nucleus. But it can't do that. It can't do that because it has to obey the conservation of mass. Meaning the mass that it starts with has to be the mass that it ends with. So it can't do that. But what it can do is it can turn one of its neutrons into a proton. And that's what happens. So as it goes from H3 into helium 3, so hydrogen 3 to helium 3, one of the blue circles turns into a red circle. You can see that clearly from the picture. Okay? However, that's not all. That's not the whole story. It can't just do that and be done. Because it turned one of its neutral neutrons into a positive proton, conservation of charge, something we haven't really learned about, but the charge has to stay the same. So it started with only 1 positive in hydrogen 3, and it ended with 2 positives in helium 3. So in order to counteract that extra positive that it gained by turning a neutron into a proton, it emits what we call a beta particle, which is just an electron. And if you remember, electrons have a negative charge. Okay? So let's write a balanced equation for this. So we start with hydrogen 3 or tritium, which is one of the isotopes, unstable radioactive isotopes of hydrogen. So I'm going to write the isotope symbol for hydrogen 3. So I wrote it right there. A mass of 3 and an atomic number of 1. It decays into helium 3 and a beta particle. So I'm going to add the beta particle later, but I don't know exactly what I need to write for the beta particle because I haven't learned it yet. I know what to write for my parent isotope because I know H is the symbol for hydrogen, 1 is its atomic number, and 3 is the mass. I also know what to write for my daughter isotope because 2 is the atomic number for helium, 3 is the amount of mass that it contains because it contains 3 subatomic particles in terms of 2 protons and 1 neutron. What do I write for my beta particle? Well, since I'm emitting an electron, I'm going to write a lowercase e to represent electron. I remember from conservation of mass that the mass that I start with has to be the mass that I end with. Well, I started with 3. I ended with 3 AMUs in my helium atom, so that means I have to have a mass of 0 for my electron, which should make sense because we remember that the electron has a mass of 0. Now the harder thing to realize is the amount of protons or positive charge that we have. We started with 1, and then all of a sudden we decay into having 2 in my helium. So if you're intuitive, you might understand that for a beta particle we have to have a negative 1 written for the atomic number, if you will, for a beta particle. So this is what a beta particle looks like in terms of its symbol. So it's a beta particle. Okay? And this is a balanced equation for beta decay. Our individual example asks you to, in the space below, write the equation for the beta decay of actinium-230. Place a box around the daughter isotope. So pause the video here and resume it when you want to check your answer. So this is a problem that we've done if you followed the video for alpha decay, but now we're doing the exact same element but beta decay. So we look for a parent isotope. It's given to us in the problem. It's actinium-230. So I write down the isotope symbol for that. So again, I know AC is the symbol, 230 is the mass, and I got to find the atomic number, and it's 89. I can find that from the periodic table. It decays into a daughter isotope and a beta particle. And I know that the beta particle is going to be an electron, -1 and 0, because that's what a beta particle is. When we say it undergoes beta decay, we automatically should be thinking E, -1, 0, because that is a beta particle. Remember, that is the symbol for beta. Okay, so now I got to figure out what I need to write for my daughter. Okay, and I know that my daughter isotope needs to have a atomic number that adds up to 89. So if I write 90 as my atomic number, 90 plus -1 will get me 89. So 90 would be the correct atomic number, and I see from the periodic table that that would be thorium. And I also need to look at my mass. I started with 230 and I need to end with 230. Since the beta particle has none, I know that the mass of thorium must be 230, and I should box in my final daughter isotope.